This is day 2 of section 8.1 and 8.2. We're going to talk about exponential growth and decay. We talked about it in the last section according to graphing, but here we're going to talk about it more in a real life kind of way. So exponential growth and decay is when a real life quantity is increased or decreased by a fixed percent each year. So here's the equation that we would use. Y equals A times A plus R to the T power. This represents a growth. This is the growth factor. It helps us find our percent increase. So in this particular case and in this equation, and see how I have the growth and decay model here from both of these two. So I'm going to go ahead and draw a line here. So this one is a growth factor because it's 1 plus the rate. The R stands for the percent, and you write it as a decimal. And I'll make all this make sense when we get down to some examples. The A represents our initial amount, or the starting amount. So since we're adding the percent, it's a growth. On the next one, since we're subtracting the percent, we call this one a decay factor, where we would say that this thing decreases. It helps us find our percent decrease. So I think I'll do a couple examples here before we move over to compound interest. So the first example on the notes, see if I can blow it up here. It says, given the following exponential function, identify whether the change represents a growth or decay and determine the percent rate of increase or decrease. So in order to tell if it's growth or decay, I have to look at this. And since this number is greater than 1, I know that I have a growth. So the growth factor is 1 plus the rate, and our growth factor is 1.01. So this means that the rate must be 0.01. And that rate is written as a decimal. So to change it back to the percent, I'm going to move the decimal 2 places. So 0.01 would mean the same thing as 1%. So on your delta math, we would want this one to be growth and a 1%. Let's look at the next one. Given the following exponential function, identify whether it's a growth or decay. Determine the percentage rate of increase or decrease. So I want to look inside here. Because this number is between 0 and 1, this is a decay. So I would go down and change this one to decay. And so now this is going to change to be a decrease. So the factor is 1 minus R equals, and ours is 0.82. So what would I subtract from 1 to get 0.82? So we would say negative R equals negative 0.18. So R equals 0.18. So since it's 0.18 as R, move the decimal 2 places, and that means this would be an 18% decrease. Okay, let's look at the last one. First thing I want to do is determine if it's a percent increase or a percent decrease. So I'm going to look inside here. This one is between 0 and 1, so it's going to be decrease. So this thing is a decay, not growth. So 1 minus R equals 0.42. So negative R equals 0.58. So R equals 0.58. So since it's 0.58 as a decimal, this would be a 58% decrease. Okay, now let's talk about how we would use this in a couple of word problems here. So let's go ahead and go to the back. And we'll do a couple here. So it says town has a population of 10,000 and grows at 2.5% every year. What will the population be to the nearest whole number? So the first thing we have to decide is if we have a growth or decay problem. And this one says that it grows, so I know that it's going to be a growth problem. And the equation for that is y equals the initial amount times 1 plus r to the t power. So A represents the starting amount, and the starting population is 10,000. 1 plus R. Our R is 2.5%. So to change that to a decimal, I move it away from the percent sign. So that would be 0.025 as a decimal. And then I want this to happen for 7 years. So I'm going to type that straight into my calculator. I'm going to grab my calculator here. So I can type it just like it says, 10,000, parenthesis, 1 plus 0.025, parenthesis, and then the exponent this time is 7. So it should look like that. So I get 11,886.857. But then I want to make sure I go back up to the problem and look and see how it wants my answer. It wants this one to the nearest whole number. So the nearest whole number would be this spot right here. So I'm going to look backwards to decide if that 6 is going to stay the same or round up. And in this case, it's going to round up. So my answer would be 11,887. So if I started with 10,000 people and it grows at this percentage rate, this is how many I would have after 7 years. You can see how this would be useful for somebody who works for the city if they wanted to project populations to know how to increase their sewer system or roads or anything like that. Okay, let's look at the next one. An element with 310 gram decays at 8.9 per minute. How much of the element is remaining after 19 minutes? So this one decays, so I'm going to use the decay factor, y equals A times 1 minus r to the t. The starting number of grams that we have is 310. And it's going to decay at 8.9%, so I have to change 8.9% to a decimal, so I'm going to move it 2 places away from the decimal. So 1 minus 0.089, and this is happening for 19 minutes. So I'm going to plug that straight into my calculator. And I get 52.748. But the problem says round to the nearest tenth of a gram. This is the 10th spot. So I'm going to look backwards, and I see that the 7 is going to stay the same. So it's going to take 52.7 minutes for that to happen. I'm sorry, after 19 minutes we'll have 52.7 grams. So we started with this much and it decayed and we were left with this much after 19 minutes. So for the next one, why don't you pause the video and see if you can work it yourself and then come back and see how you did. So this one is a growth. So it's going to be y equals 20,000 times 1 plus, and 4% as a decimal would be 0.04 every 6 years. So I get 25306.38, and it says round to the nearest whole number. This is the nearest whole number, so I'm going to look backwards to see if the 6 is going to stay the same or round up, and this one's going to stay the same. So it'll be 25,306.